to the fall 2015 FE review session for everyone's favorite subject, transportation. Sorry. All right. That's all the formalities we're going through. All right, so the transportation is covered on the FE reference handbook, and I do have screen captures in each of the slides from the current version, which is 9.3, and it's pages 168 through 175. So according to the website, there are 8 to 12 questions on transportation, and I can almost guarantee you will see something related to geometric design, either horizontal or vertical curvature will be the bulk of that, and then they're starting to throw in some of these other topic areas, and these should all be reviewed from 342. Most of these examples are the same ones that we went over in 342. So these numbers 1 through 8 are how I've got the slides laid out. So the geometric design of streets and highways, so this is going to be the stopping sight distance, and that can be applied to road segments. So driving straight down the road, somebody applies the brakes, could have a grade, how long is it going to take them, or what distance is it going to take them to come to a complete stop. We have stopping sight distance applications for vertical curves and horizontal curves as well. And so there is a surveying section, which I'm going to go over next week, but the vertical curve and horizontal curve calculations kind of include transportation and surveying applications. And then we have super elevation. So stopping sight distance. So this is the distance that the car travels while a person is making a decision to stop. And kind of we have the two components, the reaction time component, and then after they hit the brakes, the distance that they traveled during braking. And so that's more so based on the grade and the pavement friction. This is the equation on the right that's given in the equation in the FE book, and it's the same format of the equation we used in 342. If you remember in 342, we had two different versions of this equation. I referred to one of them as the old method. So this is the newer, the FE method, where you don't explicitly see that friction factor in there. But looking at the components, you have the 1.47 times VT, so that first term is going to be the reaction distance. So this here is the reaction. And then the second term is going to be the stopping distance. And so on a question, they might ask you specifically, not for the total stopping sight distance, but to throw you a curveball, they might ask what is the reaction distance, or what is only the, actually this is not stopping, this is braking. They might ask you what is the braking distance, and the total is the stopping sight distance. So if they're only asking for the braking distance, then they're only looking for the last half of that equation. And just recall this 1.47 factor here, that's just the conversion from miles per hour to feet per second, because the speed, large V down here, is in miles per hour, and then your time, reaction time T, is in seconds. So what did we assume for stopping sight distance, the driver reaction time? No. 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 Average. 2.5. So again, this is not a value that they give you in the equation book, but it's one that that you might be asked to remember, and that's the standard design value. What do we use 1 second reaction time for? Yeah, so this is applying to an open, like an interstate or an open roadway where you don't have an expectation to stop, and so it might take you a little bit longer to realize that there's something in the road you need to stop for. Also, the assumed deceleration rate, I think this is probably something they're going to give you in the problem, but if not given anything else, 11.2 feet per second squared is kind of the comfortable deceleration rate. All right, so stopping sight distance. The following design requirements exist for a section of highway with a 1.5% grade. Calculate the stopping sight distance for drivers on this section of highway. So using that same equation, stopping sight distance equals 1.47. Speed, again, we leave it in miles per hour because of that conversion factor. We're given a reaction time of 2 seconds here. And then the second part of that equation, was v squared, so 70 squared over 30, and we're not given a different deceleration rate, so we'll use 11.2 over 32.2, and then we don't have a grade, so that second part of that term drops out. Do we do anything with the driver eye height and the object height here? No. Do you remember what we use those components for? So whenever we get to stopping sight distance on a vertical curve. So it is related to stopping sight distance calculations, but not in this case since we're not given any information about a vertical curve or anything. So it's extra information that you need to be aware to ignore. So what's this give you? Anybody with the calculator? Give me the two components. In this problem, you're ignoring the driver eye height and the object height because those only apply to a vertical curve, stopping sight distance on a vertical curve.
The first one is 205.8, and the second one is 469.6. So the total was 675.4.
So our total stopping sight distance is 675.4 feet. Questions on that one? Oh, yeah. So I missed the grade there. So this is going to change this. So should we calculate for a positive 1.5% grade or a negative? Which one's going to be more conservative? The negative. So if they're going downhill, it's going to take them farther to stop. So the more conservative estimate would be to assume negative, and grade here is in percent or decimal? So percent divided by 100 would be a decimal. That's going to change this answer. So lesson 1, be sure you read the entire problem. $490. Now, any questions? All right, so stopping sight distance on vertical curve. So for a crest curve, for a crest curve, again, we have the vehicle, not a red wagon, crossing the vertical curve. For a crest curve, again, crest is the hill, sag is the valley. So this is representing the driver's eye height, so the driver being able to see across the crest of the curve to see an object on the other side of the road. So the default values for this are 3.5 feet for the driver eye height and 2 feet for the object height. For a sag curve, the night is the controlling condition, so it's really how far ahead are the headlights going to project. And so the parameters that we're interested in are the headlight height and the headlight angle, but as you'll see on the next slide, they don't provide the equations to use those inputs. So these should look familiar from 342. This is on page 169 in the FE book. But we have it gives you here that standard eye height and the standard object height for the crest curve, but for the sag curve, they just tell you it's based on the standard headlight criteria. And they're not going to ask you to memorize what the headlight default values are since they don't give you the equations to use them. So looking at these equations, we can use these to calculate what the total length of the curve should be. And if you recall in vertical curve design, the length of the curve is the horizontal distance from wherever the VPC is to the VPT. So this is the total curve length L. And so these equations we can use to calculate L. And you have to go through, this is where you calculate L, assuming that S, where S is what? Remember what S is? No, what's it stand for? Yeah, so S is actually the stopping sight distance. I'm not sure. So in the last equation, stopping sight distance is SSD. Here they use S for stopping sight distance. Just realize they're the same. So we have to go through and solve for L, plugging in our H's and A, which is the algebraic difference in the grades, and S. So stopping sight distance is going to be based on the speed, the design speed of the roadway. So we'll know all these values. We're going to solve for L. We check to see if this S is less than L, so the S that we started with is less than the L we calculated. If so, then this would be the design length. Then we go, if not, then we go through and calculate it this way, and then L should be less than S, and that would be the design length. If you're told you can assume the default values for H1 and H2, these two equations reduce to these two equations down here for that calculation. And then again, we've got A and S down here for these for the sag curve. So that's what I just mentioned. Always evaluate the two equations and determine which inequality is true. So crest curve on a section of highway consists of a positive 1% grade followed by a negative, that negative is kind of lost up here, don't forget about it, a negative 3% grade. The design requirements are as follows. Find the minimum required length of vertical curve needed to satisfy the design stopping sight distance. So we're again going to use those two equations. So the first one we want to evaluate is less than S less than or equal to L. And we have different values of driver eye height and object height to use. So our first one is L equals A. So again, is this a crest curve or a sag curve? So we have positive 1 followed by a negative 3%. So this gives us an A equal to 4 because A is the algebraic difference, not as a percentage, as a whole number. This is a common mistake on problems in 342, is converting that to a decimal. So we want that to be a whole number. So we get 4. We were told that our stopping sight distance is 1,000. So 4 times 1,000 squared divided by 100. Square root of 2. H1 was 4 feet plus square root of 2. H2 is 6 inches, so that'd be a half a foot. Those units have to be the same. And then everything there squared. So solve for that. Well, somebody's solving for that. Our next calculation, the S greater than L. Everybody got the first one? 2,729 feet. So S less than L, so actually that inequality checks out, so that's probably our design L. But just to check your work, it's good to go ahead and calculate both of them and make sure that the other inequality isn't true, because they shouldn't both be true. Yeah, so that S is, so this one is not the correct one. Mhm. So that would be, so the minimum length would be our 2,729 feet. Questions on that one? Should be on slide 14. No, there's a page number.
In case of first volume,
Seemed like the first volume, we didn't add the grade in. We considered grade when we saw for an answer. Would the answers? among
We
the
did.
first one,
We did after it got corrected.
Would they be really close like that to deceive you? You know what I mean? In case, like, let's say you got to apply the grade to the equation. Would you see it?
Oh, I'm sure.
Would you likely see
Oh,
it?
yeah. Yeah, all the incorrect multiple choice answers they give you on the FE exam are well thought out. So if there's a common mistake to be made, and you're more than likely going to see that answer there that's common for that mistake.
there's probably one with a plus to it as well.
Yeah. And for this problem, I'm sure you would see 1634 as well as 2729.
So if we do have a problem like that, and if that's LS positive or negative grade, we should just subtract.
You should assume whatever one's more conservative. So in terms of stopping sight distance, more conservative is going to be the higher value. So that's always going to be downhill. Yeah. All right, stopping sight distance on a horizontal curve. So here the application is the driver is going around the turn. You've got some sort of obstruction on the side of the road because their sight line is across the curve. They're not, unless they're eye bender or something, they're not going to be looking along the center line of the roadway for an obstruction. And so the value that you're calculating is the HSO, or the horizontal sight line offset. So that is the distance measured from the object itself, whether it's a trees or a sign or a cut section of rock. The distance from that perpendicular to the center line of the inside lane. So if you have, it's always to the center line of the inside lane is going to be your controlling scenario. So you have this equation here on page 169, where R is the radius of the horizontal curve. S, again, is your stopping sight distance. So you will calculate that HSO value. So this example, two-lane rural road has a 10-degree horizontal curve extending for 750 feet along its center line. The road is 20 feet wide with 2-foot wide shoulders. The design speed for this road is 50 miles an hour. Find the required horizontal sight line offset for this curve so that the trees can be removed from the edge of the road. So we got a lot of information here. Ultimately, we're wanting to calculate HSO is equal to R 1 minus cosine 28.65, is that right? Times R over, what was it, so I don't have to flip back?
28.65 S over R.
No, S over R. And we get a bracket. All right, so R is going to be equal to what? So we have enough, we need to know what is the radius R. So we haven't gone over the horizontal curve yet, which I think is, let me jump ahead to look at those equations. So the radius, we need to find one of these that we can use to solve for the radius. So we know the degree of curve, so yeah. So we've got a, we know the horizontal curve is a 10-degree curve, so we can use that 5729.58. So R is equal to 5729.58 divided by the 10 degrees. I can do that one in my head. We'll call it 572.9. Stopping sight distance, what does that equal to? How can we find it? It's not given. So stopping sight distance, 1.47. Our design speed is 50. What should we assume is the reaction time? 2.5 plus 50 squared, 11.2 divided by 32.2. And we don't have any grade information, so we'll assume there's no grade. So plugging everything in. So we'll call it 38.7 for that horizontal side offset. So in this case, we didn't, since we're just asked to calculate the horizontal side offset, we didn't really have to use the width of the road or how wide the shoulders were, but they might give you that information and ask you how far from the edge of the road or how far from some other point of reference on the roadway, but you just realize that the HSO is measured to the center line of the inside lane. Questions on that one? Oh, so actually, yeah, you're right. So if, I'll just show it as even though you normally don't have passing lanes on a curve, but the HSO is measured from here. So the total road is 20 feet wide, so how wide does that make the lanes? So that'd be 10 feet, and then you've got, so from the edge of the road, depending on whether you call the edge of the pavement or the edge of the shoulder, we'll call it from the edge of the pavement. So this would need to go an additional 28.7 feet. So that 10 feet gets subtracted here. So it'd be 28.7 feet from the edge of the road. Well, that's what I said. It depends on whether you assume from the, the question isn't specific enough to know whether it's from the edge of the traveled way or the edge of the shoulder. But the question on the FE would hopefully be a little bit clearer. Depends on if it's paved or not. If it's a paved shoulder, I would do it from the outside of the shoulder, but if it's just a gravel shoulder, I would do it from the edge of the pavement.
Does it really make a difference? That's a decent suggestion.
It's been a long day. Vertical curve. So this is on page 171 in the FE. And so this is just depicting the crest vertical curve, but the same calculations apply even if it is a sag vertical curve. One thing that is kind of missing from this is that all of the vertical curves that you're probably going to see are equal tangent vertical curves. So that means the distance from the PVI or the VPI to the VPT or PVT is L over 2. And the same thing from the VPC to the VPI is L over 2. So that's important whenever we're calculating stations and elevations of the VPC. Because typically, when you're laying out a vertical curve, this is your starting information, and then you're working off from that to calculate the VPT and the VPC. The main equations that you want on here, so this one that I'm pointing at here in red, I'll point at it again in red, or maybe I'll use blue because I can. This is going to give you the elevation of a point on the curve. So if you're asked what is the elevation here, again, if you imagine this is kind of a XY set of XY axes where your Y is your elevation and the X is the station or the distance along the curve. So this first term, the Y PVC, is basically what's the elevation of this PVC point here. The second term, G1X, that is projecting along this line, and it technically goes all the way to the PVT. And then the third term, I'm running out of colors. The third term is the parabolic offset, which if that's what we're interested in, that's going to be a negative term for a crest curve, and it's going to bring that elevation back down to the curve itself. So that's a pretty important equation. Also, the K equals LA. This is the shortcut method, but in order to use the shortcut method, you're typically solving for L, which is the length of your curve. A is the algebraic difference. K, you would need a table, and the FE reference manual does not give you that table, but they could give you the table as part of the problem, and I'll go over or show you that table here in a couple slides, or one slide. So this is, again, L equals Ka, the equation, and then this is from 342. You got your design speed increasing, and then you have the K factor specifically for the crest and the K factor for the sag. So you're going to know for your curve what's the first G1, and G2 to give you A, and then look up K corresponding to the design speed and quickly calculate your curve length. So again, you're going to see at least one of these problems, possibly two, because it's such a common thing to have on the FE exam. Again, you're typically going to get the VPI station elevation, have to calculate everything from there, which could be the elevation at the PVC, the PVT, the station of those, the station or elevation of a point on the curve, and also the high-low point on the curve. Forgot to circle that one. Yeah, so you can use this equation to calculate the horizontal distance. So this is going to give you the horizontal distance to the high or low point on the curve. Then once you get that distance x, you plug it into this equation to give you what is the elevation of the high or low point on the curve. So the biggest mistakes on vertical curve problems, so in 342, I always used the grades as decimal, not as a percentage, and then the distance units x as feet, not in stations. You can also do it in percentage in stations, but I think it gets a little confusing. So keep your grades in decimal format and your distances in feet. A back tangent with a plus 7% grade meets a forward tangent with a negative 5% grade on a vertical alignment. So is this a sag curve or a crest curve? So this is, yeah, so if the back tangent's plus 7, so it'd be plus 7 coming towards the VPI, and then we have the negative 5 going away from it. So we've got our VPC, our VPT connected by a curve. And we have our overall curve length L. We have 1,150 foot horizontal length of curve, so we actually know that L is equal to 1,150. And we're given the station and the elevation of the VPI or the PVI. So first we want to find the station and elevation of the PVC. So PVC station is going to be equal to, again, we know this is this distance from VPC to VPI along the X is equal to L over 2. So if we start with our PVI of 2035 and subtract L over 2, that will give us the station of the PVC, which is 14 plus 60. Likewise, we can do the PVT station, 2035 plus 1150 over 2. So these two equations aren't really explicitly given to you, but hopefully you can figure it out by looking at the picture. 2610. So now we have the PVC elevation. So again, we're trying to find what is this elevation difference. So starting at our VPI elevation of 250, and we're going to subtract. We know what the grade of this, of the back tangent is, and we know the horizontal distance between those. So if we take 0.07 times 1150 over 2, that'll give us the change in y. Same thing with the PVT. Only this time we're subtracting 0.05. What is it?
221.25.
Any questions on either one of those? Fix that. It's supposed to be in that. So now at station 21 plus 35, we want to find the elevation on the curve itself. So before we can do that, we have to determine what is x. So we find that by taking 2135 minus the station of our PVC. What did you say it was? So 675 feet. So is this on the left side or the right side of the VPI? Yeah, so it's probably somewhere in here because it's a little more than half of 1150. So calculating the y at 21 plus 35. So we start off with the elevation of our PVC, which is 209.75, plus G1X. Again, we want it in decimal. X is 675, and then plus G2 minus G1. So make sure you're all, for this equation, you definitely want to keep the signs on the G's. G2 minus G1 over 2 times L, which is 1150. And don't forget the X squared on the end. Very easy to leave that out. So we know this answer should be roughly between what two numbers? Yeah, so it's certainly going to be somewhere between the PVC elevation and our PVI elevation, which is 250. So if you make a gross calculation error, you're going to get something out of those bounds and you know that it's not right. Anybody got anything? What makes it approximately 232.5, somewhere in that range. So then the last is finding the station elevation or the high or low point. So is this equation going to give us, in this case, a high point or the low point? The high point. So a crest curve, it finds the high point. Sag curve, it finds the low point. So our x high is equal to, what was it, G2 minus G1 divided by, it was close, not really. So G1, and you do want to keep the signs, because they should drop out. So G1 so minus a negative becomes a positive. So this should give us an answer somewhere between 0 and 1150. So those are the bounds. So 670.8 feet. So then to find the elevation, we're going to take that number and plug it back up into this equation. So we would replace 675 with 670.8 to get the elevation. You don't need to go through that calculation. Questions on this one?
I'm drawing a blank on your first X calculation, why you took 2130 minus 1460.
So we know the station at this point that we're interested in is 2135. We know the station at the VPC is 14 plus 60. So we want to know x. So here x is equal to 0. We want to know what is x equal to at this point. So that's just the difference between those. Other questions? Yeah. Everybody get it?
Did you plus that other 675 at the end, or did you keep it?
Yeah, both of them. Which, yeah, so it ends up being the same. Yeah, it's pretty close to it. It's only 4 feet away. Questions?
That is the same thing, it's the same point, it's just off by like, that 5 feet isn't making any difference in the equation.
Okay. So you're saying next time around I should pick a different to make it more interesting.
Say 25, decision 25.
All right, horizontal curves. So they give you pretty much every equation you could possibly imagine related to horizontal curves, except for the ones that are pretty important for calculating PC and PT. So again, this is horizontal curve looking down on the curve. We always start at the PI and back calculate the PC by taking PI minus this tangent distance T. So that's what this first equation is. So that'll give you the PC. But then to get the PT, we do not take the PI plus the T because we want our stationing. We want to know what's that stationing along the curve itself. So we have to go back to the PC, then calculate the stationing along the curve L, so that's why we're adding L to the PC to get the PT. So they do not give you those equations, but I'm pretty sure that's a common problem they ask, is to calculate what's the PC station and the PT station. So yeah, if it's not clear, these are stations. I'm sure it's still not clear since I wrote so small and illegibly. Yeah. All right, horizontal curve is laid out with the point of intersection at station 22 plus 0, 0, a radius of 1,000 feet and an intersection angle of 120 degrees. So again, this is mostly plug and chug. So we've got our PI up here at 22 plus 0, 0. We have a radius of 1,000. And the intersection angle, where is that? Yeah, so it's up the top. It's also down here. So obviously this isn't drawn to scale. So this would be 120 degrees. So we want to find the degree of curve. So D, this is the very first equation on the sheet, is 5729.58 divided by 1,000. So our degree of curve is going to be 5.729 degrees and some change. And hopefully everybody remembers how to convert to degrees, minutes, seconds in case they have the answers in degrees, minutes, seconds. Handy button on your Casio FX115 ES Plus. I don't have the Plus. Is that an extra 30 cents at Walmart to get the Plus? Really? Nice. All right, tangent distance. Equation for tangent is R tangent I over 2. So I is our intersection angle. What is it? That's good enough. L, there's a few equations for L. I think I over D times 100, we have that information. So 120 over 5.729. I guess technically, if I'm going to round it, it'd be 2095, not a big deal. So then we can calculate our PC as 2200 minus T, which is 1732. $468. And then our PT is going to be equal to, actually this is 4 plus 68 as a station. So then we have 468 plus L to get our PT station. Three?
No, I used 2025, that's what that was.
So that's 2562 for our PT station. So they could ask you the middle ordinate, the external distance. They could ask you pretty much any parameter on there. It's just going through and finding the correct equation to use. Should be pretty straightforward. Everybody get that? If not, go watch the video. Additional horizontal curves. I don't know if degrees versus radians is a big deal on those calculators, but we're using some trig functions on the last ones. You can also calculate super elevation. So again, super elevation is the parameter E here. So if you've got your car coming in and out of the roadway, and this is a horrible picture, but coming in and out of the screen. Well, they're like the NASCAR tires. You're looking at it coming head on, so they look really square coming head on. And to have this much super elevation, it'd have to be a NASCAR track, right? So what? Maybe it's going the other direction. If we could be standing behind it, it's going away from us.
Unless you got smoke in your face.
Nobody likes to.
You can visualize what the super elevation is. I'm not giving you any help. All right, so actually I am. So if we've got two sides of the equation, so the super elevation and the friction is what's holding the car in, and then the other component, the speed, is what's trying to push the car out. So the friction factor, and they're probably going to give you, they don't give you the friction factor table in the textbook, or sorry, in the FE equation book. So they might give you a friction factor to assume, or they might ask you what is the combined super elevation and friction factor needed to keep a car in the from sliding off the curve at a certain speed and a given radius. We also have the spiral transition. So imagine what it is, because I'm not drawing the picture. No. So if we have a horizontal curve, the spiral transition, if we have a tangent section leading up to it, again, kind of the way I describe it in 342, if you don't have a spiral transition, as soon as the car gets to the PC, you're going to instantly turn your wheel to kind of match the radius to navigate the curve. A spiral transition starts out at a radius here of infinity and then spirals to match whatever the radius of your actual curve is. So it's more of a gradual turn. In the original basis for that, they use spiral transitions in railroad design because a train can't instantly turn its wheels or it would derail. So they build in the spiral transitions so that it will turn around the curve itself. So this calculation, this equation, is what allows you to calculate the length. So the total length of the spiral would be this. So L sub S is how long that spiral needs to be. So you've got the speed and then the radius of the curve, and then C you would assume to be a value of 1 unless otherwise stated in the problem. Yeah, so that's still the uppercase V. And so, no, velocity here should be in miles per hour because it's the uppercase V. So they've got the conversion factor, because L does give it to you in feet, but this conversion factor is that's handling the conversion from miles per hour to feet per second. So a two-lane railroad has a 10-degree horizontal curve, same one we saw in the problem earlier. What is the super elevation needed to give a side friction factor of 0 at the design speed? So we're basically looking at the right side. What was it, 2R? No, 30R. 30 divided by 2. That's what I meant. Yeah, we'll look at it. We're going to calculate it here in a second. So we're looking at, if we assume a side friction factor is 0, so this term's going to drop out. So we're really solving for E here. So E is going to be equal to this is uppercase V, so it stays in miles per hour. Yeah, yeah. That's just assuming it's in a whole percentage and converting it to a decimal. That's the only thing that's doing. So this is going to give us the decimal format. So we have 15 squared over 15 times our radius. And if you look back, I think our radius is 572.9 for a 10-degree horizontal curve. So we would need a super elevation of 29%, which is really high. Is that really what it gives you? Did you get anybody else verify that? Okay. Yeah, so obviously solving, because the friction factors are somewhere in the 0.12 to 0.30, so if you're going to neglect friction, so if this was a road of ice, I guess you would want a super elevation of 29% for people to maintain 50 miles an hour around the curve. All right, so spiral curve, so L sub S is equal to, what was it? V cubed squared over. So C we'll assume is 1. So since it is an uppercase V, we keep it in miles per hour. So we would have 50 cubed 13. So at 50 miles an hour, 13 feet, you might as well not even have a spiral curve.
572.9.
So I bet 13 was an answer, because if you squared instead of cubing. What is it, 687? So that'd give us a transition as longer than what our actual radius of the curve is. That answer your question? Yes. Other questions? Pavement design. So again, this is something else we covered in transportation. The load equivalency factor / ESEL, I think the FE exam uses the LEF, load equivalency factor. We also refer to it as an ESEL in 342. And there is a table on the next slide that gives you what those load equivalency factors are for a given axle weight. There should be another bullet here. This should be on the next line. So the other application for pavement design is calculating the structural number of the pavement based on the layer thickness and the given coefficients. And just a reminder, kind of the pavement design assumes you have the subgrade, which is the existing foundation, which has a depth of infinity. But then we've got D1, so the asphalt is on top. Then we have the base, which is D2, and then the subbase, which is D3. So we can solve for the thicknesses of those 3 layers. This is the table for the load equivalency factors. So you've got the weight. Notice this is axle load, and so we're dealing with pounds. And notice down here it goes to 40,000, and then the table continues over here. So this should be, if it was a single table, it would go on down the page, so don't get confused. Then we also have a column for single axles and a column for tandem axles. So one thing to note is that the tandem axle is the total weight. So it's going to have 2 axles, but the weight that's referred to here is the total weight sitting on both of those axles, not the total weight divided by 2, which would be the individual axle that's part of the tandem. And then on this same page, page 172, we've got the structural number equation. So let's look at the structural number calculation first. The flexible pavement system is to be designed using the AASHTO structural number design method with the following criteria. If the minimum thickness of surfacing, so the minimum thickness, so 2 inches of asphalt, and the minimum thickness of base, which is 4 inches, what is the required thickness of the subbase? So just using that equation, SN equals A1 D1 plus A2 D2 plus A3 D3. So this entire term A1 D1 gives you the structural number of that specific layer. So getting the overall structural number for the pavement, we want so down here, this should be up here in the problem. If we assume the design structural number is 2.5, so that's what we're trying to achieve. And if you remember that ugly nomograph that we used in 342, that nomograph is what would give us the 2.5. So we know we need, based on the traffic load and the conditions and all that stuff, we need 2.5. So then we've got our strength coefficients, 0.44 times 2 plus 0.25 times 4 plus 0.10 times D3. D3, we get 6.2 inches, and we would probably, since it's a subbase with large aggregate, we would round that up to 7 inches. So the structural number problems shouldn't get very complex because they're definitely not going to give you the nomograph. The only thing that you have to work off of is that structural number equation. But if they tell you it's only a 2-layer pavement and you only have a surface and a base, then this term just drops out. And then you've got your A1, your layer 1 and your layer 2 information. Questions on that one? So now calculate the load equivalency factor of a loaded Class 9 truck that has a front single axle transmitting a force of 10,000 pounds and 2 sets of tandem axles, each set transmitting a force of 3,000 pounds. So for our Class 9, we have a single, 2 tandems, got the trailer,
It's got one really small wheel.
it's going flat. All right, so our single, we have 10,000 pounds, and then a total of 3,000 or 30,000. So if they gave you the individual weights of those axles within the tandems, you would want to add those together so that we get the overall. So our total LEF is going to be equal to what? So 10,000 pound single axle, what is its 0.08? So we have one of those. And then for the 30,000 tandem, we have 2 of those. So this would give us a total load equivalency factor . Pretty straightforward. Traffic safety. So this is calculating crash rates. For intersections, we're interested in the rate per million entering vehicles, so vehicles, the number of vehicles actually entering the intersection. For a road segment, so if we've got a road segment that's a certain length, L, we're interested in the total VMT, the rate per 100 million vehicle miles traveled. So that's more like a VMT, since the length of the roadway segment is important. We can also determine the number of crashes that will be prevented if a certain countermeasure is installed, and we have equations from both of those. So page 175, and they just updated this in the most recent version, web version 9.3, 9.2 had some errors in it. But we have the RMEV, so they tell you, they didn't used to have this row in here, so you kind of had to know which equation applied to intersections, which equation applied to road segments. Kind of surprised they added that. But here A is the number of crashes in a single year. So if they give you 3 years worth of crashes, you need to divide that number by 3 because this needs to be for a single year. Then we're multiplying times 1,000,000 and divided by V, where V is the ADT times 365. So this is giving you a yearly volume. So you're taking ADT, which is an average daily traffic volume, multiplying times 365. The RMVM, so I think there should be an H in here because it's per 100 million, rate per 100 million, so that would actually go here. But notice that we're multiplying it times 100 million. Our MVM implies that it's million, but we've got 2 extra zeros here. So then the denominator is the VMT, so we've got the length of the road built in, the ADT, and then normally this is going to be 365 again, assuming you're looking at 1 year of data for A. Then down here we have the number of crashes prevented. So this is the expected, and then we have a crash reduction factor, and then you have the ADT after the improvement divided by the ADT before the improvement. So if they're going to go out and install a traffic signal or extra guardrail or something like that, that will have a crash reduction factor corresponding to it. So an intersection had 13 crashes last year. So since it's an intersection, we know it's an RMEV. So we had 13 crashes last year. The 4 legs of the intersection had 2-way ADT values of 9671. I'm not going to write them all out, but these are 2-way values, which is important because we have to, since those are ADTs, that's both entering and exiting volumes on each approach because an ADT is going both directions. So we want to divide each of those by 2 because we only want the volume entering the intersection. So we're going to have 13 times our million plus 9671, or divided by 9671 plus 2893 plus 9506 plus 2611 divided by 2. For oh, we forgot something. That's daily. We forgot the 365. Is it 12,341 after you divide by 2? Yeah. So divide 1,053 by, that sounds better. So that's 2.89 crashes per million entering vehicles. That would be a lot of crashes. It'd be like treating this intersection out here, telling everybody they can go through driverless and just take their hands off the wheel and feet off the brakes. 6.1 mile section of roadway had 6 crashes last year, so now we're RHMVM or RMVM for a segment. So we have 6 crashes times 100 million over the VMT, which is going to be, now we do want the total traffic going in each direction. So we want the 755 times 365 to get the yearly, and then times the segment length, which is 6.1 miles. 356. Did I leave a term off? Is that right? Close enough. Did I get all the terms? That sounds high as well. Yeah, that's it. Stay off that roadway. So questions about crash rates. So then the crash reduction. So we're calculating, there's not a term for the crash reduction, or not a variable, but our crash reduction is going to be N times our crash reduction ADT after, is that right? After, over, before? All right, so first we have 3 different countermeasures. We need to combine those because we can't, if we just add them together, we can't have a crash reduction greater than 1. So our combined crash reduction is going to be equal to 0.40 plus 1 minus 0.40 times 0.28. Is that right? Plus, what's the next one?
1 minus 0.28 times 0.2.
That doesn't sound right.
1 minus 0.4 times 1 minus.
Okay, that sounds better. I definitely wasn't expecting to check the football score and see that it's 2-0.
Yeah, it's a lot of time. What's that? 0.65.
So now we have 3 years of crashes. So we just want to average those in this case. So we get an average of 13 times the crash reduction of 0.65. ADT after is expected to be 9,000 divided by 7850. So we would expect 9.7, 9 or 10 crashes reduced, which is pretty good considering we're averaging 13. So we would only expect there to be 4 remaining.
3 of the river.
Yeah, can never get rid of those. Traffic flow and capacity. So these charts should look somewhat familiar. This is the traffic flow relationship. So this is the base one up here, the speed and density. So again, the concept, density, when density is low, there's like 1 car on the road. So that car is going to be driving at free flow speed. As the traffic gets denser and denser, cars get closer together and they start slowing down. So we have that negative trend. Then we have the speed flow relationship over here, and then the density flow relationship. So what they used to have on here that they no longer have on here is this basic relationship here. So in 342, I think we use Q equals U for speed and K for density. And so the units, so flow rate is typically in vehicles per hour. Speed is in miles per hour. And then density is vehicles per mile. So the units work out with that equation. So here the equivalent would be V equals DS, and that's a pretty basic relationship that they could expect you to remember. The other relationship you can see here, where is it? V sub M is the maximum possible flow rate, so it shows up in both. So the maximum flow rate, we also referred to that as capacity. We called it Q max, which with these terms would be V sub M. What is it equal to? How do we find Q max? So building on this equation, so V, what free flow or max flow rate occurs at what speed? So D naught, which is DJ divided by 2, so it occurs at SF, so half of the free flow speed times half of the jam density. So the free flow speed times the jam density divided by 4. So that's another relationship that you can kind of look at the charts and see it. Mean speed on a road is given by the relationship V equals, and sorry, this should be D for density. V, so this should actually be S for speed. So this is a speed density relationship, 60 minus 0.2 times D. If the mean speed on the road during rush hour is 45 miles an hour, find the density of vehicles on the road. So again, this is looking at this relationship. So this equation tells us that this value is 60 miles an hour, so that first term in that's going to be the y-intercept in that term, and then the slope of this line is negative 0.2. So if we know that the speed at one particular location is at 45, this is 45, we're just looking for the corresponding density. So solving that equation, 45 equals 60 minus 0.2 D. D is what? Determine the maximum capacity of traffic volume for this roadway. So using the terms here, VM equals DJ SF over 4. So we know what SF is, 60. How do we find DJ? So DJ is where the x-intercept is. How do we find the x-intercept of this equation? Yeah, so 0 equals 60 minus 0.2 D. So D sub J, 60 divided by 0.2. So we would have 300 times 60 divided by 4. That is a lot of vehicles. I'll assume that that is not a per lane. So there's some multiple lanes that are being accounted for here. Questions on that one? Everybody got it? This was vehicle signal change interval, so we have the yellow time and the all red time. Again, the all red time is after, not the entire time that a movement is red, but the time when one yellow ends and the next green starts. So here, we talked about this earlier, what driver reaction time do we assume? So 1.0. Length of vehicle in class, I usually tell you to assume 20. The 25 that you used in class today was to account for the vehicle plus the gap between it if they were sitting queued up. But for the all red interval, we assume 20 feet. Notice that this gets calculated to the 10th of a second, and also I've got notice that this is little v, so it's looking for the speed to be in feet per second in these two calculations. A, I don't call out A here, but A, you can assume 11.2 feet per second squared, similar to the stopping sight distance where we saw A. So yellow is going to be 1 plus, if we have 40 miles an hour, already forgot it, 40 times 1.47 to convert to feet per second squared, no, is it squared? V over 2A, no square, divided by 2 times 11.2. We don't have any grade, so we can neglect that. 3.6 seconds for the yellow. He didn't stop. Again, this is a result of converting from narrow to wide and not checking the animation. Yeah. Red clearance. So we have W plus L. So W here is the intersection width that the car needs to clear. So we're given 72 plus the length of the car, assumed at 20, divided by 1.47 times 40. See if he makes it out of the intersection. Oh, yeah. .6 seconds. Transportation planning. We're on the home stretch. So the only two I think that I'm going to talk about. So trip generation, there's not really anything they can give you because this is where you use the chart. Like for a gas station, how many pumps are there? If there's 3 pumps, we're estimating this total trips that are being generated. I guess they could give you that chart and ask you to do some calculations, but hopefully you can remember how to do that. So trip generation, assuming you have the city broken down into these different census tracts, trying to estimate how many like shopping trips are going to be generated from one zone going to other zones. And so the gravity model is what we can use to estimate those particular trips. So this is from page 174. And so T, there's a lot of variables on here, but for the most part, the K value is ignored, so that drops out. And you really have the A, the number of trips attracted to a particular zone, and F, which is related to the travel time. So the larger the travel time, the less trips it's going to have. And A, the number of trips being attracted, we used in class the population as a representative. So the example from class was how many shopping trips from Huntington are going to go to each of the Barboursville Mall, Charleston Mall, and Columbus Mall. And so the logic with using the population was that larger cities are going to have better shopping opportunities and more malls and things like that, and are therefore going to be more attractive, but they have the longer travel time, which is going to kind of offset that. So the friction factor, again, this is the factor F on the previous slide. So we're going to calculate the friction factor of these, which is just 0.7 times T, where T is in minutes. And this equation is just one that happens to be given for this problem. They would give you one, and that should be a -2. This is not T minus 2, 0.7 times t to the negative 2 power.
And 1.9 times 10 to the
1.9.
Yeah.
All right, 4.
Yeah.
So now to calculate the trip distribution. So the trips to Barbersville. So P in that equation is the total number of trips that are being generated, which we're given in the problem is 10,000. Then our numerator is going to be A, which in this case is the population. So our A for Barbersville is 3183 times the friction factor for Barbersville divided by the A and the F for all three. So we would have 3183 so Barbersville plus Charleston plus Columbus. So the denominator for all three of these calculations would be the same. So it's just the numerator that you would swap out when you go through and calculate the T for Charleston and the T for Columbus. But this equation here is the actual gravity calculation equation from the previous slide. You close? We don't need to calculate all of them. Times 10,000. Just multiply, get the 10,000 at the beginning.
29.42.
So 2,942 trips are going to go to Barbersville, and then the remaining would be going to Charleston and Columbus, but in the interest of time, we won't calculate each of those. Any questions on this one? Everybody got that? Mode choice. So this is trying to pick between bus, personal car, plane, walking. So there's two equations. So this logit model or utility function, this would exist as an equation for each mode, and then you're going to plug in the attributes. So X here is the attribute, could be travel time, cost, or others. And then once you calculate the utility, so you'd have the utility of the auto, the utility of the bus, and utility of walking, whatever parameters you have, then those U's get plugged in to this equation to calculate the percentage of the population that's going to be taking each one. So this example was looking at the office park where they're trying to estimate the percentage of bus riders based on, are they going to drive their own car, or are they willing to take the shuttle bus? And so we have this equation. It's our utility equation. We are given each parameter for plugging into this equation. So we would have utility for the auto is 0.73 minus 0.47. There's no out-of-pocket cost for the automobile, even though really there's gas, but we're going to ignore that in this problem. and then minus 0.22 times the travel time of 10.5. Likewise, we'd have the utility of the bus, which doesn't have an initial term, minus 0.47 times 75 cents, which is the fare, and then minus 0.22 times 18 for the travel time. They should be negative. Yep.
The first one's negative 1.58.
So generally, if you have multiple options, the highest number is going to get the largest share. So it's going to be the preferable one. So we already know that the auto is going to have the highest share, but to calculate the actual percentage, we're going to take e to the, this would be the percentage of auto. This would be e to the negative 1.58 over e to the negative 1.58 plus e to the negative 4.31. What is it? Yeah, I think that sounds right. So we have 94% taking the automobile. The other 6% would be taking the bus, since it has to total 100. If you had 3 options, you could go through and calculate 2, where the denominator is going to be the same for all these calculations, and then you just swap out the numerator. So this is the answer to the first one. What would the bus mode share be if the bus fare is reduced to 0? So the only thing you would do there is cancel out this term and recalculate the utility, and then plug that new utility in here to recalculate the percentage. So we should see that percentage of the bus increase, since it now all of a sudden becomes free. You can do that for homework. So any questions on this one? And I think that brings us to the end of transportation.
How are we getting all this?
I don't know, but don't go through that. Don't drive on that road segment that has 3,000 or 300, crash rate of 300.